Okay, I need to do two more problems that go with the solving exponential equations. And these are a special case. What I can do is, if I can get the bases to be the same, then all I have to do is set the exponents equal to each other. I can rewrite 125 with the base of 5. It is 5 to the third power, because that gives us 125. Over here, I'm left with 5 to the 3x minus 1. Now that our bases are the same and we're saying that this equation is equal, the left is equal to the right, this is going to imply, if the bases are the same, the exponents have to equal each other. So I can set these two equal to get to each other and then solve for x. I'm going to take the one to the other side by adding it. So I'm going to get 3x equals 4. Divide by 3. And x is equal to 4/3. I can check my answer. If I take 4 and divide it by 3 and I store it under x, okay, if I plug it in right here, it should give me 125. So 5 raised to the 3x minus 1, and hopefully it gives us 125, and it does, so I know that answer is right. Over here, kind of have to remember your exponent rules, okay? I can rewrite both of these with bases of 3. Like this one right here, 27, that's the easier one. I can rewrite that as 3 to the third power raised to the x. Over here, because my 9's in the denominator, that means my exponent is negative. So I can rewrite that as 3 to the negative second. Now, raising a power to a power, you multiply your exponents. So this really is 3 to the negative second equals 3 to the 3x power. Now, our bases are the same, so this implies that we can set our exponents equal to each other. Divide both sides by 3, and x is equal to a negative 2/3. So to check that answer, okay, negative 2 divided by 3, store x. Let's see if I can get it to where you can see it a little bit better. I got a glare in here, sorry. We'll just have to leave it right here. Now I'm going to type in 1/9. Well, it doesn't really matter. Actually, I'm going to type in, hit this, 27 raised to the x power, which in this case is 2/3. And because I need it to be a fractional answer, I'm going to hit math fraction. Oops, and I get a syntax error. Let's see what I did. Go to it. Oh, of course. Let's use my arrow key. Now we need a fractional answer. And then I get 1/9. So I know that answer checks out. Okay, that finished up those. So what you want to do on these type problems is try to get the bases the same. And if you have the same base, then you can set the exponents equal to each other. Okay. The last section, exponential function applications. We always end everything with applications. All right, so we're fitting exponential models to data using it to make a prediction. Okay, so they give us 3 graphs, 3 figures here, and you have to pick the one that fits best. It says which curve fits the data best. See all these blue dots? That's our data, okay? Move this over so the whole thing's in there. There we go. Okay, obviously this curve hits the majority of them. It's the best fit. So that's the one we're going to use. Y equals 66 times 1.12 raised to the x power. Okay, so now we're going to use this equation of best fitting curve from part A to predict the value of the item at let's try this again, at a time 15 years after its purchase. Okay, well, up here, I didn't read this part. Y is in dollars and X is time in years. Well, they give us 15 years, so we're going to plug the 15 right here. Y equals 66 times 1.12 raised to the 15th power. Because again, this is our dollars and this is our years. Just like everything else, we just read the problem to know what our X and our Y is. Okay, so all you have to do is plug it in. It is 66, 1.12 raised to the 15th. And Y is in dollars, so it is $361.26. Says to the nearest hundredth, which is 2 decimal places. Okay. Hold on, it's not wanting to cooperate there. Okay. When we do exponential functions, we always talk about growth and decay. And I think we kind of already hit on this earlier in one of our other sections. Okay, so we have these two formulas. The value A represents the initial amount and is the y-intercept because of this, all right? When you raise anything to the 0 power, it becomes 1, so A times 1 is A. So basically, A is our initial amount. The value B is called the growth or decay factor. Okay, so if B is greater than 1, it represents a growth. And values of B between 0 and 1 represent a decay. Okay, so if you have a fraction or a decimal, it's going to be a decay. If it's greater than 1, it's going to be a growth. So the growth factor is related to the rate of change. These are the ones we actually used before. If it's a growth, you would use the plus. If it was a decay, it'd have minus. That's where the number between 0 and 1 comes in. And this is where it's greater than 1. All right. The price of a certain item is X years old is defined by this. What is the initial price? This is your A. So the initial price of the item, I'm assuming is in dollars, 300. Is it an exponential growth or decay? Well, what you're going to look at is this right here. That is greater than 1, so that represents a growth. Okay? That is 1 plus our rate. That's what that stands for, the 1 plus R. Because it says, by what percent does the price change per year? Well, if you take 1, okay, or looking at this, how much over 1 is it? Well, it's 0.08 over the 1, which represents 8% because you move your decimal 2 places. Okay? Right here, it gives us a price of a certain item is X years old is defined by this. What is the initial price? Again, the initial is what's in front, so it's going to be $523. I'm assuming these are in dollars. They don't really tell us. Is it a growth or decay? Well, because of this, it's less than 1. It's a decay. And what percent? Well, what's the difference between 1 and this? The difference would be 0.08, which again, in this case, it's 8%. The only difference is this was a decay and this was a growth. So now we'll go to some problems here. It says Susie has a petri dish with 350 bacteria. I really feel like we've done this in another section. I know we did, but we'll go ahead and do it again. They are growing at a rate of 17% per day. Define your variable rate function. Okay, so because they are growing, you are going to use the f of x is equal to it's going to be this one right here because it's a growth. A is the initial amount. In this case, our initial amount was $350. And it's going to be 1 plus R, this as a decimal, so it's going to be plus 0.17 raised to the x power. So we just need to combine that, and we get 350 times 1.17 raised to the x power. Right here, Peter has a petri dish with 550 bacteria. They are dying, so that's going to be a decay. So instead of adding here, we're going to subtract at a rate of 9%. Okay, so we're going to have, I'm just going to call it f of x. They don't really tell us, so we'll just use f of x. Our initial is 550. 1, and because it's decaying, it's dying, we're going to subtract it, and this written as a decimal is 0.09 raised to the x power. Now this gives us 550. We just have to subtract this right here, and we get 0.91 raised to the x power. I kind of went up on that. I don't know why I couldn't write straight, but apparently I could. And that's all. Evaluating exponential function with base e. Okay, so we're going to talk about this formula right here, which we've seen before. This is our continuous compounding formula. Laura wants to buy a bond that will mature to 6,000. Oh, the difference here is now we want to know how much we have, I think how much we have to put in. Yeah. Laura wants to buy a bond that will mature to $6,000 in 6 years. How much should she pay for the bond now if it earns interest at a rate of 3.5% per year? Okay, so we're going to change that. 0.35. Compounded continuously. Round it to the nearest cent. That means we're going to use this formula. There is another formula that we learned earlier. I'll give you both formulas. You just have to know when to use which. The other one would be like compounded monthly, compounded daily, and so on. Okay, so it's compounded continuously. The amount A, okay, that is, we want $6,000 at the end, so we're going to put 6,000 equals, we don't know how much we have to put in. That's what we're wanting to find out. E, our rate is 0.035 times our time, and time is always in years, and in this case it was 6 years.
Here's what I found.
Oops, my watch is picking me up. It says continuous compound interest. Siri never answers when I need her. Okay, times 6. Okay, so that's the formula, rate times time. Okay, what I need to do first is I want to do this part here first. So I have 6,000 equals P times E raised to the 0.0, oops, let's try this again, 0.035 times 6. And we get 0.21. Okay. Now we are trying to solve for P, so all we're going to do is divide by E to the 0.21. So now we take our calculator and we just do 6,000 divided by our E raised to the 0.21, and she will need to pay $4,863.51 for the bond right now to end up with 6,000 in 6 years. Okay, I'm going to stop right there for a second and I'll do another video for the next one.